Welcome to Hot Chips 26. Session 1, High Performance Computing.
So before I hand over, I'd just like to thank the amazing crew we have who pull Hot Chips together. I was general chair, but I had to do very little thanks to a very experienced, very professional team here. Amazing set of volunteers. And the program committee did a fantastic job putting that program together. They'll be up in a minute. I'd also like to thank all of our sponsors, especially our platinum sponsors, Intel and Oracle. They help to keep the registration costs low and help subsidize all the student reg fees. We thank them for that. If you would like to become a sponsor for next year, please contact us. We'd love to have you on board. So finally, I'd just like to hand over to our program co-chairs, Sam Nafziger and Guri Sohi, and they'll introduce the technical program to you. Okay, and finally, thanks to all the attendees for coming here. It should be a great conference. Bye.
Thanks, Krista. So welcome to Hot Chips 26. I'm Sam Nafziger from AMD, and this is my colleague, Guri Sohi from University of Wisconsin. We are very proud of the program we put together this year. 26 years of innovation presented at this conference. A look back over those 26 years show the amazing progress made in computer engineering. The progress can be measured in terms of performance, cost, density, versatility of function, all these dimensions. And these advances have brought dramatic new capabilities, creating new companies, new markets, and even new patterns of socialization. So the Hot Chips Conference, it's a platform to record these advances year by year, and it's a record of these advances and the communication of ideas that enable future improvements. Some have stated that hardware innovation has slowed down and that ideas are tapped out. I beg to differ. A look at the breadth of innovative designs, architectures, and products in our program this year shows a vibrant ecosystem of hardware innovation that's driving technology forward faster than ever. So in our program this year, we see a particularly rich set of advances covering special purpose ASIC designs to high-volume general-purpose processors. We have exciting developments in mobile processing and servers and FPGAs, new applications and architectures. So we appreciate your full engagement during these sessions. Audience questions and interaction are key to making this as informative and interesting as possible. So without further ado, I'd like to introduce the chair of our first session today, Pradeep Dubey.
Thank you, Sam and Guri. So we begin our Hot Chips conference this year right at the mountaintop. That means at the highest end of performance. So our first session is on high performance computing. And the very first talk is by Dr. Shintary Momose. Momose is a manager of high performance computing development at NEC. He heads the department that's developing SX vector processing, vector supercomputers for NEC, responsible for marketing, business development, and system design of SX vector supercomputer. And he has been focusing on what we often call ninja gap, meaning how do you design a high sustained flop supercomputer without the programming difficulties, something that can be programmed easily. He received his B in mechanical engineering and master's and PhD in information science and at Tohoku University. So let's welcome Momose.
Thank you, Chairman. Good morning, ladies and gentlemen. I am Shintary Momose of NEC Corporation IT Platform Division from Tokyo, Japan. And today I'd like to introduce our brand new vector processor, SXACE processor. At first, I'd like to introduce our SX history and technical evolutions. NEC has always provided the high sustained performance vector supercomputer SX series. Our first machine was SX1 and 2 that was launched 1983. Therefore, last year was our 30th anniversary of SX vector business. And last year, we also launched the SX8 vector supercomputer. And today, I'd like to focus on this SX8 processor. And these are today's my presentation. At first, I'd like to introduce HPC technical trends and issues, and SX8 processor design direction against these issues. And then I'd like to introduce processor architecture, the SX8 processor architecture and the core architecture and implementations, and especially focusing on memory subsystem in order to provide higher sustained performance or higher sustained memory bandwidth. And third one is performance evaluations. Experimental results of several memory-intensive benchmarks will be shown, and finally, conclusions. And the introduction. I'd like to introduce HPC technical trend and issues. And this figure shows the trend of top 500, especially top 10 systems average. And the blue line shows the impact growing rate. This is twice per year. And this is number of cores per system. And this is number of nodes per system. And this is Moore's law, growing rate. And this is single core performance. And this is the processor frequency. And as this figure shows, the single core performance and processor frequency have become nearly constant. However, Moore's law, this is very high growing rate, 1.42 times per year, have been kept. And this higher growing rate has been provided by increasing number of cores per processor. And as you know, this is a many core approach. Moreover, please note that this impact growing rate is much higher than Moore's law growing rate. And this much higher growing rate has been provided by increasing the number of cores per system or increasing the number of nodes per system. This is massive power approach. And such massive power approach, in order to achieve higher sustained performance, user must spend their time to extract massive parallelism from their own code. And we think that the big core can provide the big core, which is the higher performance core, can reduce the utilizing number of cores. This is one of our approach. And this figure shows the required memory bandwidth in their applications. And this figure is reported by a Japanese government. And each dot point indicates each application, and x-axis shows the required memory capacity, and the y-axis shows the required memory bandwidth measured by byte per flop ratio. And the byte per flop ratio is a balance between memory bandwidth and peak performance. And as this figure shows, the lower side of this figure with lower byte per flop area, this area is computation intensiveness area. And today's scalar CPUs like x86 or some kind of accelerators can cover this computation intensive area. And NEC also has a scalar product like a PC cluster or some kind of accelerator product. However, the upper side of this figure, memory intensive area, cannot be covered by today's commodity scalar CPUs. And our design direction, SX8 processor design direction, is to cover this memory intensive application area. And these are the concept of our SX8 vector supercomputer. We would like to provide the best solution for memory intensive applications against scalar processor trend. One big concept is big core. And big core is high-performance core, and which can reduce massive parallel difficulty with fewer cores. And the big core can provide the world top class performance, which is 64 gigaflops with the largest memory bandwidth, 64 gigabytes per second per single core in average, and in the maximum case, 256 gigabytes per second memory bandwidth can be enjoyed by a single core. And the SXA's vector supercomputer can provide lower power consumption. We would like to provide the best memory bandwidth solution in power consumption point of view. And the memory bandwidth per watt, gigabyte per second per watt, compared with x86 CPU, 1.8 times higher. And moreover, we can provide a hybrid solution, vector supercomputer, SXAs, with a scalar supercomputer with x86 processors. Tightly coupled environment can be provided by our specialized softwares. And from now on, I'd like to introduce our architecture. This figure shows our SXA's vector processor overview. There are 4 cores. This yellow part are cores. And the single core consists of 3 major parts: scalar processing unit, SPU, and vector processing unit, VPU, and assignable data buffer, ADB. And the SPU works as a scalar process, works as a VPU controller. Vector instruction is issued from SPU to VPU. And vector processing unit provides 64 gigaflops vector performance. And the ADB is like a vector cache, and the capacity is 1 megabyte. And the ADB bandwidth between ADB and VPU is 256 gigabytes per second. And each 4 core connected to this memory cluster with 256 gigabytes per second memory bandwidth. And this cluster is connected to 16 memory controllers with 256 gigabytes per second memory bandwidth. And each memory controller has 1 DDR3 memory interfaces. Therefore, 16 memory controllers can provide the 256 off-chip memory bandwidth. And in the case of 4-core running, memory bandwidth per single core is 64 gigabytes per second in average. Moreover, in the case of only 1 core running on this processor, one core can enjoy 4 memory bandwidths of 256 gigabytes per second. This is a very big feature of this processor, and this configuration can accelerate serial part in parallel processing, which has a memory intensive type. And there are 4 cores implemented into this processor LSI, and the performance reaches 256 gigaflops, and the memory bandwidth 256 gigabytes per second, and the memory capacity also large. This is 64 gigabytes. And this is a single core comparison between our SXA's single core and today's scalar processors, Xeon E5, Xeon Phi, and the GPGPU, and PowerPC, and the SPARC64. And the blue bar indicates double precision performance per core, and the red bar indicates the memory bandwidth per core. And as this figure shows, our SXA's processor, single core, can provide the highest DP performance and the highest memory bandwidth per single core. And this is the floor plan of the SXA's processor. We designed this processor with memory access focused layout. And there are 4 cores with each ADB. And there are 16 DDR3 interfaces are implemented both sides of the processor. And this is memory crossover, and this is connecting these 16 DDR3 interfaces and 4 cores with 256 gigabytes per second memory bandwidth. And utilized process rule is 28 nanometers, and the clock speed is 1 gigahertz. This can reduce the power consumption. And the die size is 23.05 by 24.75 millimeters. And approximately 2 billion transistors are implemented into this processor. And there are several interfaces, 16 DDR3 interfaces. And the IXS, this is dedicated interconnect interfaces, and 2 channels of PCI Express interfaces are implemented upper side of this processor. And here I'd like to introduce core architecture, details of vector architecture. And this figure shows a single core configuration. Single core consists of 3 major parts. One is ADB, and one is SPU, and vector processing unit, VPU. And VPU consists of 16 vector pipeline processor, VPP, from VPP0 to VPP15. And one VPP has 2 other pipelines, 2 multiply pipelines, and 1 divide square root pipeline, logical pipeline, and mask pipeline. And there are 3 major vector registers. One is vector data register, 64 sets, 256 elements each, and the vector mask register for mask operation, vector mask operation, and the vector arithmetic register, which is directly connected to these pipelines. And data is loaded from memory or assignable data buffer to vector data registers with interleaved manner. Number 0 is VPP0, and number 1 is VPP1, and number 15 is to VPP15. And this vector data register holds these 256 vector elements until process is started. And the fan process is started, data is forwarded to from vector data register to vector arithmetic registers. And therefore, the one VPP holds 16 data sets in the VPP0, for example, VPP0, and the 16 vector data is processed with 16 clock cycles. Therefore, 256 vector operations by one vector instruction is processed by 16 parallel with 16 vector pipeline processors and 16 clock cycles in the each vector pipeline processors. And these 16 clock cycles can hide memory access latency or instruction issuing latency. This is a very big feature of SX vector processor. And this figure shows the single node configuration of our predecessor, SX9. This is predecessor, and this is SX8. SX9 has 16 CPUs, and 1 terabyte capacity memory is here. And 1 terabyte memory and 16 CPUs are perfectly connected as a UMA, Unified Memory Access configuration. And this powerful configuration can provide very high sustained performance. However, over 70% power is consumed by this powerful memory access configuration. And in order to reduce the power consumption, this powerful memory access configuration is integrated into one CPU LSI. Therefore, in the case of same performance, 1.6 teraflops and 1.5 teraflops, the number of LSIs are drastically reduced from 516 to 6. And the power consumption also drastically reduced 1/10, from 30 to 2.8. And this is the memory subsystem connecting between CPU core and the memory interfaces, memory controllers. And the red line indicates the load direction, and the blue line indicates the store direction. And there are 4 cores and 16 memory controllers. And the 4 cores and 16 memory controllers are connected with equidistance as a SMP or UMA configuration. And we also try to reduce the DRAM energy. DRAM activation powers strongly depends on the cache line size, as this figure shows. Cache line size is 64 bytes, 128 bytes, and 256 bytes. And the larger cache line size can reduce the DRAM activation power consumption. However, sustained memory bandwidth is strongly affected by adopted cache line size. And in order to provide adequate cache line size with balancing power consumption and sustained memory bandwidth, the SXH processor supporting 64-byte and 128-byte memory access granularity. And 128-byte as a default to reduce power consumption, and 64-byte for sparse memory access such as stride and indirect memory accesses. And this is detailed assignable data buffer. Assignable data buffer is on-chip cache for vector architecture, and the private type per core and 1 megabyte capacity, and for set associative and 16 banks are implemented. And they're customized for fast random access. And this assignable data buffer big feature is assignable feature. A bypass flag is implemented into each vector memory access instructions. And the compiler or user inserting directive can control the bypass flag. A data is stored ADB or not, can be controlled. And this feature can avoid cache pollution effectively. And the misstatus holding register, MSHR feature, also implemented in order to avoid the redundant memory transactions. And moreover, in order to improve the sustained memory bandwidth, we implement the out-of-order vector memory access functions. For consecutive memory access and stride memory access, hardware can control the overtaking among vector instructions, vector memory access instructions. For consecutive memory access, hardware checks lower bound and upper bound of each vector memory access. For example, vector store, vector load A, and vector load B. Vector load A has overlapping with precedent vector store. Therefore, this cannot overtaking. And vector load B have no overlapping with precedent vector store. Therefore, this load operation can overtaking. And stride memory access also handled by hardware. Hardware checks start address and stride. And in this case, vector load B has no overlapping with precedent vector store. Then this vector load B can overtake precedent vector store. And for indirect memory access, software features implemented. Vector overlapping flag, VO flag, is implemented into vector scatter or vector store instruction. And the compiler or user can control this vector overlapping flag. And if vector overlapping flag is enabled, subsequent vector loads can overtake this vector scatter or vector store. And this is implementation. CPU is here, and 16 DDR3 DIMMs are here, and the card size is 11 centimeters by 37 centimeters. And the hybrid cooling is implemented, is adopted in order to optimize the cooling efficiency, and rack weight. Rack weight is very important. And CPU is cooled by water flow. CPU is here, cooled by water flow, and other components like memory are cooled by air cooling. And the performance evaluation. We evaluate sustained performance by 3 benchmark programs. For off-chip memory bandwidth, stream triad. For off and on-chip memory bandwidth, Himeno benchmark. And for indirect memory access performance, Legendre transformation kernel are utilized. And optimization by only compiler optimization. And the performance comparison between our predecessor of SX9 and SX8 and IB Bridge Intel Xeon and IBM Power 7 and Fujitsu FX10. And as this list shows, the SX8 and other 3 scalar processors processor performance basically same. However, the number of cores and memory bandwidth and the power consumption. This power consumption is from rated rack power consumption. It's divided by number of CPUs per rack. And at first, I'd like to introduce the evaluation of off-chip memory bandwidth evaluated by stream triad benchmark. And as this figure shows, there are only 1 core running on the processor case. Only SX8 can provide the full memory bandwidth. Other scalar processor cannot provide the full memory bandwidth, 1 core or 2 core or 3 core. And in the case of full memory bandwidth is provided, SX8 can provide 4 times higher memory bandwidth compared with other scalar processors. And the power efficiency point of view, SX8 can provide 2 to 5 times higher power efficiency compared with scalar processors. And this is the evaluation of off-chip and on-chip memory bandwidth with Himeno benchmark, which is highly memory-intensive type. And the left side is performance. SX8 can provide 4 to 17 times higher sustained performance compared with scalar processors. And the right side is power efficiency. SX8 can provide 2 to 25 times higher power efficiency compared with scalar processors. And this is the indirect memory access evaluation. Legendre transformation is utilized. And please note that in this evaluation, data size is 4.4 megabytes. Therefore, scalar processors can hold all data into their caches. And for sustained performance point of view, SX8 can provide the highest performance. However, the power efficiency point of view, IB Bridge can provide the highest power efficiency. This is because this code is very strongly cache effective, and the IB Bridge power consumption is lower compared with other scalar processors and SX8. However, the SX8 can provide the higher power efficiency compared with Power 7 or FX10, which are designed by a cache-based architecture. And the conclusions. Issue of modern scalar and accelerator products, massive power with small cores, and low memory bandwidth. And our SX8 design direction is providing the big core with large memory bandwidth and improving problem vector architectures. And the SX8 processor has 4 cores, and each core has 64 gigaflops single core performance with 64 gigabytes per second memory bandwidth in average, and 256 gigabytes per second in the maximum. And the efficient memory subsystem for higher sustained memory bandwidth. And the performance point of view, higher sustained performance and power efficiency for memory-intensive benchmark kernels can be provided. And finally, I'd like to express my gratitude to Cyber Science Center at Tohoku University Supercomputing Center, the joint research project with our NEC Corporation. Thank you very much for your kind attention.
We have time for a few questions. Please state your name and affiliation and ask the question.
My name is Tadao Nakamura of Cool Chips Conference Series. Generally speaking, do you have a capability to increase the memory bandwidth much more?
If we utilize like a GDDR5 or HBM, we can improve memory bandwidth much more. However, the memory capacity is relatively small. And this is a very big issue for supercomputing.
Okay, so far as you use existing memories, for example, even though that's SRAM, DRAM, that has a limitation of speed. And probably that has very big issues for thermal problems, power consumptions. So memory should be increased in future, I think. Thank you.
Thank you very much.
Hi, Chris Drasanovic, UC Berkeley. I had a question about the indexed store operation, the SCADA, where you had the overtaking bit. When can software read the values that were stored by that SCADA? How does software indicate I now want?
Hardware takes long time to check dependency between indirect memory accesses. And if user allows the overtaking, user knows the precedent indirect memory access and the subsequent memory access is no dependency. User can check the VO flag, and the subsequent memory access can overtake.
So how many subsequent vector accesses can overtake? Just one or more than one?
No. 32 or more. 32 vector memory access or more.
Okay, and you indicate this in the instruction, how many future loads do not depend on the store?
Yes. We have a, yes, your question is good. We have some kind of interrupting.
A fence instruction?
Yes, stopping the overtaking, yeah.
Okay, thank you.
More questions?
Over here?
Go ahead.
Over on the right, or your left.
Yes.
I'm curious about the hybrid cooling approach you're using in slide 19. In particular, is it really just water you're using or some other coolant? And is it a closed system? How does that work? By the way, I'm Nathan Brookwood from Inside64 for people who don't know.
CPU is, your question is?
On the cooling.
Cooling, yes. Portion or?
Well, two questions. One, is it water or some other coolant? And number two, is it a closed system? Where does the cool water come from? Or where does the hot water go to?
CPU heat is removed by water flow, and the other components is cooled by air flow. And about 50% rack heat is removed by water, and 50% is removed by airflow. And second question is?
And the question is, when the hot water comes out of that module, what happens? Is there a radiator in the rack? Does it go externally, or what?
Water cooling CPU is go back to chiller and the heat exchanger, and the primary water is supplied from facility, and the heat is exchanged to primary water, and the primary water is cooled by some kind of chiller.
And is that chiller in the system, or is it up on the roof?
Roof or machine room, implemented into machine room.
Thank you.
Fantastic. Let's thank our speaker one more time.
Thank you very much.
Our next talk is by Fujitsu, next generation processor for high performance computing. Speaker is Toshio Yoshida. He's director of LSI development division at the next generation technical computing unit of Fujitsu. Toshio started working on SPARC64 in year 2000. So for last 14, 15 years, he has pretty much worked on most SPARC machines, SPARC chips you can think of. The SPARC8FX was #1 and top 500 in 2011. He received his master's in physics from University of Tokyo. So Toshio.
Good morning. I'm Toshio Yoshida. I'm a director at Fujitsu, next generation technical computing unit. Thank you for coming to this session. I'm very excited to have an opportunity to introduce the SPARC64 Xlfx, Fujitsu's next generation processor for HPC. My presentation consists of 3 parts. First of all, I will show you the recent history of the processor development at Fujitsu. Secondly, the majority of my presentation will be in-depth discussion of the SPARC64 Xlfx, starting with the design concept and chip overview. I will explain node architecture and enhanced ISA HPCS2, as well as the microarchitecture of this chip. And I will explain some unique function of Fujitsu's HPC processor, VISIMPACT, sector cache, and assistant core. I will talk about the performance and RAS as well. Finally, I will summarize my presentation and have a time for questions. This is the recent history of the Fujitsu processor development. In the last year, I made a presentation about the SPARC64 10+, which is now used in the Unix server called Fujitsu M10. Today's topic is the SPARC64 Xlfx. This is the enhanced successor to the SPARC64 9FX, which we developed for the HPC systems. We consider this processor to be a groundwork for the exascale supercomputing, so we implement some major change from the K computer. Now, let's move on to the SPARC64 Xlfx in depth. First, I will start with the design concept and processor overview. This slide shows the design concept of the SPARC64 Xlfx. This processor is designed for massively parallel supercomputing systems, which enables high performance for the wide range of the applications. Of course, high scalability and low power consumptions are vital. We position this processor as a groundwork for exascale supercomputing. And we enhanced and inherited the K-computer features, including the standalone and identical scalar many core architecture. We also enhanced the VISIMPACT and sector cache. And we used the TOF interconnect tool, which was introduced in the K-computer, and we successfully integrated the TOF controller into the chip. Furthermore, we introduced a the following new technologies useful for the exascale supercomputing. Enhanced ISA, named HPCS2, provides a wider SIMD enhancement. We employed the leading-edge memory technology, Micron HMC, to realize the extremely high throughput. This chip has 2 assistant cores dedicated to the non-computation operations. Take a look at the die photo of the SPARC64 Xlfx. This chip includes the 32 computing cores on the both sides and 2 assistant cores in the center with a 24 megabyte level 2 cache. HMC and TOF2 PCI Gen 3 controllers are embedded on the chip. This chip is fabricated in the state-of-the-art 20-nano CMOS process with around 3.7 billion transistors. The chip speed plans to be 2.2 gigahertz. The peak performance reached 1.1 teraflops. Memory throughput and TOF2 throughput reaches 240 gigabytes per second and 125 gigabytes per second for input and output, respectively. Now, let me talk about the node architecture of the SPARC64 Xlfx. Node of the SPARC64 Xlfx is a standalone type and consists of the identical scalar many core with wider SIMD. We have no accelerator. The memory architecture is non-hierarchical 32 gigabyte memory capacity with a high bandwidth by utilizing the 8 HMC modules. We isolate the non-computation operation from the computing cores to reduce the jitter. This chip includes the 32 computing cores and 2 assistant cores. Assistant cores can handle the daemon, I/O, and MPI synchronous communications. Sector cache, which was introduced in the K computer, is used for the assistant core to avoid the cache pollution. Of course, computing core and assistant core keep cache coherency. Single operating system manages the computing and assistant cores, so that can help to minimize the memory management overhead in the case of the communication of computing cores and assistant cores. Let me explain HPCS2, the enhanced ISA. This slide lists the main enhancement point of the HPCS2. HPCS2 realized a wider SIMD enhancement from the K computer. This HPCS supports a 256-bit wide SIMD. And in addition, we added the mobile integer operation on the SIMD registers. To handle the discrete data on the memory, we introduced the straight memory access as well as the indirect memory access. To deal with the if sentence more efficiently, we added the compress instruction, which can aggregate the vector element whose masks are true value. We vectorize the rounding operation to speed up the built-in function. Permutation instructions can perform the vector element manipulation. In the few next slides, I will show the performance effect by the HPCS2. HPCS2 provides the 256-bit bitwide SIMD that can handle the 4 vectors of the double precision and 8 vectors of the single precision. This bar graph shows the performance, normalized performance compared to the SPARC64 Xlfx in the basic kernel, such as Broadcast or DuxPy. SPARC64 Xlfx realized 3.2 times faster in double precision and 6.1 times faster in single precision. This is due to not only the wider SIMD, but also some improvement of the L1 cache control and higher frequency. Built-in functions are also accelerated by the HC26 instructions and some microarchitectural enhancements. As you can see in this graph, 25 bits not only 256 bits wide SIMD, but also the rounding, bit manipulation, and exponential auxiliary instruction contribute to the performance. HC26 introduced the stride memory access. Stride access is frequently used in the various HPC applications, such as complex number and multidimensional variables. HC26 supports the stride access from 2 to 7 element stride width, and 3 times faster than the SPARC64 Xlfx. HC26 also supports the indirect memory access for the list accesses. List accesses appears in a wide range of HPC applications. HC26 can perform more than 1.6 times faster than SPARC64 Xlfx. That's all for the HC26. So now, let's move on to the microarchitecture. Fundamental pipeline, here is a simple diagram of the SPARC64 Xlfx Core Pipeline. And the fundamental pipelines, such as a superscalar, autoborder, branch prediction, and integer operation, are based on the SPARC64 10+, the high-end core microarchitecture. But we remove the multithreading function from the core pipeline because HPC applications has a high instruction level parallelism in contrast to the business applications. The red portion indicates the main enhancement points from the SPARC64 Xlfx. Main enhancement are SIMD FMAS and SIMD memory accesses. Now let me talk about the many-core architecture. For many-core architecture, how to connect multiple cores is a crucial issue. SPARC64 Xlfx is divided into two groups, named core memory groups. We call it CMG. Each CMG consists of the 17 cores, level 2 cache, and 2 memory access controllers. 2 CMG keeps cache coherency by CC-NUMA protocol with on-chip directory. CC-NUMA protocol enables to reduce the memory latency within a CMG. Of course, you can use the full 32 GB memory if you want. But to maximize the performance, I will recommend you to the binder process within a CMG. SPARC64 Xlfx has a high bandwidth in cache, memory, and TOF2. This chip doubles the L1 and L2 cache bandwidth per core. As a result, BF ratio of the of the core remains the same with the SPARC64 Xlfx. This chip uses the 8 HMCs. The interface of each HMC and CPU uses 15 gigabps and 16 lanes. TOF2 uses the 10 ports in total, and each port uses 25 gigabps and 4 lanes. HMC and TOF2 interface realize a much higher throughput than the standard interface as a DIMM and PCI Express. Before going into the performance and RAS, I would like to explain some unique function of Fujitsu's HPC processor, VISIMPACT, sector cache, and assistant core. Hybrid parallelization is a technique of combining the MPI and thread parallelization. The advantage of it is to reduce the communication cost in highly parallel program, and to increase the user memory space by reducing the communication buffer for MPI. VISIMPACT, which was introduced in the FX1 before the K-computer, this represents the automatic parallelization technology by Fujitsu compiler and hardware assist barrier for fast synchronization. SPARC64 Xlfx enables the 8 set of the hardware barrier between the 32 cores. Optimum combination of number of threads and the number of process depends on the applications. SPARC64 Xlfx can support any combination of the threads and process, such as 16 threads by 2 process or 8 threads by 4 process, and so on. Our future goal is the heterogeneous hybrid parallelization for load imbalance and multiphysics. I will show you the effect of the VISIMPACT. The bar graph on the left side, left side shows the normalized memory usage. By reducing the communication buffer for MPI, less process leads to the lower memory usage. This means user can use more memory space. And the bar graph on the right-hand side shows the normalized performance. By reducing the MPI cost, communication cost, some application with high cost for MPI increase the performance significantly. Let me talk about the sector cache. Sector cache replaces the cache line to keep specified sector size when cache misses occur. Like a local memory, sector cache can leave the reusable data on the cache. But this is the cache, so unlike the local memory, there is no need for the dedicated address. And of course, you don't need to save and restore any data in the context switch. SPARC64 Xlfx supports the 4 sectors in level 1 cache per core and 4 sectors in level 2 cache per CMG. It is more usable than the SPARC64 Xlfx of 2 sectors. And each sector can be specified separately. Now let me talk about the assistant core. As I mentioned, assistant core serves the daemon, I/O, and MPI synchronous communication instead of the computation. Each CMG has an assistant core allocated on the 17th core. Sector cache of the level 2 cache allocates one sector to the assistant core to avoid the cache pollution. Assistant core can minimize the performance degradation in the large system by jitter reduction, as you can see in this graph. Now let me talk about the performance. SPARC64 Xlfx boosts the performance up by the ISA and microarchitectural enhancements. In DRAM, SPARC64 Xlfx realizes the 97% execution efficiency. This is very high efficiency in the teraflops class processor. This is due to the well-balanced microarchitecture and the sector cache. Sector cache of the level 1 cache realizes the same effect as the increase of the level 1 cache size by 2.5 times. This graph shows the performance, normalized performance compared to the SPARC64 XIfx in the real HPC application, such as fluid dynamics and molecular dynamics. As you can see in this graph, 256 not only 256-bit SIMD and indirect memory access, but also the out-of-order and HMC throughput contribute to the performance improvement. On average, ISA and microarchitecture enhancement improve the performance by 33% and 40% respectively, totally 1.7 times faster than the SPARC64 XIfx. Let me explain the RAS. RAS represents the reliability, availability, and serviceability. Large-scale HPC systems require the extensive RAS capability of CPU and interconnect. SPARC64 Xlfx inherits the mainframe-level RAS features, which are summarized in the left table. The RAS circuit for this is the same as our mainframe CPU and the SPARC64 10+. Number of checkers in CPU is increased to the around 93,000. The diagram on the right-hand side graphically shows the RAS capability of this chip. Most of the chip area is green. Green means 1 bit error is correctable. This extensive RAS capability of this chip guarantees the data integrity and enables large-scale systems to keep on running. Okay, let's summarize this presentation. SPARC64 Xlfx is the Fujitsu's latest SPARC processor designed for the massively parallel supercomputing systems. We enhanced and inherit the K-computer features, including the standalone and scalar many-core architecture. We enhanced the VISIMPACT and sector cache, and we integrated the top 2 controller into the chip. Furthermore, we introduced the new technologies useful for the exascale supercomputing, such as the HPCS2, HMC, and Assistant Core. SPARC64 Xlfx has improved the performance of the real HPC applications significantly. As a next step, Fujitsu goes forward to the exascale supercomputing. That's all. Thank you. Thank you for your attention.
We have time for a few questions again.
Hi, I'm Sanjeev from Oracle. I have a question about your wider SIMD 256-bit related to memory accesses. What is the extra bandwidth you provision for that? First part. Second is, did you provision anything in the L2 cache or L1 cache sizes in order to avoid the thrashing because of that?
プラスアルファのバンド幅はいくらぐらいでしょうか。バンド幅について。
About the HMC? No, sorry. Bandwidth about the.
Your question is about the bandwidth?
Bandwidth.
Yeah, so I just want to know quantitatively what is the extra bandwidth you provisioned for supporting 256-bit SIMD in your processor?
Sorry.
256ビット SIMD をサポートするためにどれぐらいのバンド幅を提供しているという質問。
As you can see in this graph, okay. Each core the bandwidth of the level 1 cache provides 64 byte and the 32 byte, and we use the HMC, so the bandwidth is 2245 Gbps for input and output. Does this answer?
My point was that from the previous generation, when you did not have 256-bit SIMD, when you went to this processor for provisioning that SIMD, how much extra bandwidth in terms of percentage you provisioned in designed micro-architected into your processor?
We double the bandwidth per core, and the memory bandwidth is more than the doubles.
Okay. Tadao Nakamura Core Chips Conference Series. I would like to confirm that you are challenging to get extra supercomputers using these processors?
No, this is pre-exas. Yeah.
Okay, I think that's very hard to realize the extra supercomputers.
Yes.
So far, you built the K. K is 10 peta.
Yes.
Okay?
Yes.
Very high speed. And X is 100 times the speed of K. Yes. So to implement such a computer, even though that impact, that could be okay. But I think that could be very, very, very difficult to build up. So because even though you mentioned the top is a network switch. Okay, the controller embedded in the chips.
Yes.
The concept is okay. However, as a total system, okay, to build up the EXA, very, very difficult, I think.
Yes.
So you must make an effort towards such a supercomputer system.
Thank you.
Okay, comments?
Two questions for you.
Can you introduce yourself, please?
Pardon?
Just introduce yourself.
Hi, I'm Dave Weaver from Oracle. In a core processor group, you have 17 processors. One of those is an assistant core.
Yes.
Is the assistant core identical to the other cores?
Identical.
Okay.
Yeah.
And the second question is for your indirect loads, how wide are the addresses for each of the loads?
How wide? For indirect memory access, use the four vectors of the 64-bit address.
Each address 64 bits?
64-bit, yes.
Okay, thank you.
Mark Tomley with Microsoft. So it seems like you, because of the choice of HMC, you have a low memory capacity, 32 gigabytes. what do you do to provide more memory per node?
各ノードにエクストラメモリーがあるということですけど、どうやってできましたか？ノード。各ノードにメモリーオーガナイゼーションを説明してくださいということです。モード、node for each node.
Sorry.
Please repeat your question.
Well, so HMC is good for high speed and low latency, good power efficiency, but you claim you only have 32 gigabytes of memory, right? So do you provide access to remote memory, second level of memory, or is that it?
No hierarchical memory.
No hierarchical.
So user should to divide the application into the 32 gigabyte within the 32 gigabyte memory.
32 gigabytes chunks.
Yeah.
Okay, thank you.
Okay, let's thank the speakers. And thank you, Gary, for volunteering for the interpretation help. Our next and last speaker of the session is Adam Burtz. Adam Burtz at Anton, and the next talk is on Anton 2, second generation ASIC for molecular dynamics. Adam is an architect and head of physical design group at DE Shaw Research. His bio is interesting. He spends a great deal of his time fighting physical fundamental laws of physics, such as the slow speed of light and laws of thermodynamics, Murphy's laws, and such laws. Adam received his PhD in computer science from University of Wisconsin-Madison and his bachelor's from Urbana-Champaign. And he has contributed to the development of multiple processor technologies, including Pentium and Power 7. And last but not the least, no one has proven so far that he's responsible for any silicon bug in any of these processors. Adam.
Thank you, Pradeep. Good morning. I'm pleased to present to you today on the Anton 2 chip, which is our second generation ASIC specialized for molecular dynamics supercomputing. As all of you, I'm sure, know, building a chip is a difficult endeavor, so I am here representing our entire hardware team. Oh, thank you. So this is our entire hardware team. This includes all of the functions of architecture, logic and circuit design, design verification, physical design, and mechanical engineering. So it is a large group of people, but not maybe as large as you might think for a project of this complexity, which I will get into. So before I talk about what exactly we did, I'd like to tell you a little bit about what molecular dynamics is and why we've spent our time generating not one, but two custom processors for that problem. So molecular dynamics is simply the simulation of the dynamics or the motions of all atoms in a chemical system, and in our case, a biochemical system of interest. And like many physical simulations, this involves cutting up time into discrete steps. For us, it's about 2 femtoseconds, and determining all of the interatomic forces between all pairs of atoms in this system, and then integrating those forces to determine how the atoms move. Now, why is that interesting to us? It's because biochemistry is an interesting problem, and hopefully by doing this we can understand more about the biochemical machinery of the cell and learn how to modulate its operation. So why it's an interesting problem is because it's a tremendous computational task. Efficient parallelization of the task is difficult because there's a lot of communication and the individual time steps are sequentially dependent. In addition, it's just a massive quantity of computation. Interesting biochemical systems, this is a very small one here, can have hundreds of thousands to millions of individual atoms, and interesting processes in biology can take time scales of milliseconds. So at 2 femtosecond time steps, we're talking about a lot of computation. 10 to the 12 time steps at something like 10 to the 4 operations per step is not uncommon. So what we've done to tackle this problem is specialization. And we started with Anton, our original foray into this field 5 or 6 years ago. And this is kind of how we tackled the problem. We have 2 specialized computation units. One, the high-throughput interaction subsystem, as its name implies, determines the interatomic forces between pairs of interacting particles at high throughput. The remainder of the computation, which involves computing distant interactions and bonded interactions and other type of forces, as well as coordination, happens in the flexible subsystem, so named because it is a more programmable unit that deals with the rest of the computation. So in addition, when you're building a parallel machine, you also need ways to connect computation units together. And so besides the two compute subunits, we also have links in each of the 6 Cartesian directions, positive and negative on 3 axes, to adjacent ASICs in the system, and then interfaces for memory. All of this is connected by an on-chip ring in our original processor. And this was a tremendous success for us. We vastly moved the goalpost, or significantly moved the goalposts for performance in molecular dynamics simulation. And so Anton 2 inherits a lot from its progenitor. However, it inherits a lot more of it. Anton 2 delivers increased speed and throughput, as well as a much simplified model for programming and using the machine. Here on the right is a table comparing some of the main features of Anton and Anton 2. And what you see is we have a lot more compute units. Number of CPU cores has gone up by more than a factor of 4. Interaction pipelines has gone up by not quite the same factor, although in Anton, these are divided into 2 different classes of pipelines that compute 2 different kinds of forces, whereas in Anton 2, all of these pipelines are equivalent. Clock frequency has gotten a significant boost. The clock frequency of the individual cores has gone up more than a factor of 3, and even a significant bump in the frequency of the specialized arithmetic pipelines. Overall, the peak throughput of the machine has gone up by more than a factor of 4. So Anton 2 delivers over 12 fixed point operations per second. We used fixed point arithmetic because of the higher arithmetic density that it delivers. In addition to the improved speed and throughput, we also have a great deal more capacity. The capacity of an individual ASIC in terms of the number of atoms that it can store has gone up by about a factor of 18, from 460 atoms per node or ASIC to over 8,000. And the communication bandwidth that we can sustain between ASICs in the system has gone up by a similar factor, from 600 gigabits per second to 2.7 terabits per second per ASIC. In addition to all of this, I mentioned the ease of programmability. In Anton, these 13 cores were of 2 different kinds, 2 different instruction sets, and had different features, which made for a very difficult programming model. For Anton 2, all 66 of these cores are converged on a single ISA that we designed in-house, which is compiler targetable, and we've optimized GCC to target this ISA, and in addition, it provides a lot of special purpose programming extensions, or ISA extensions, which I'll touch on in a few slides. Overall, the architecture looks like this, and comparing with the figure that we saw of the original Anton, you'll recognize some of the similar elements. We have the flexible computation subsystems and the high throughput interaction subsystems. However, 2 things are immediately notable as differences between this and the Anton 1 architecture. First, there are a lot more computation units, and they are tiled. And the tiling aids both the physical design and the on-chip communication performance. The second aspect that you'll notice is that the on-chip network is no longer a ring, which can't sustain the kind of communication bandwidths and latencies that we require among the various computation units. Now we have a full on-chip routed mesh network, symbolized by these routers and the links between them. We have retained, obviously, the torus links and a memory interface, although rather than having private interface to off-chip DRAM, and a separate CMOS digital host interface, now we combine both of those functions with a PCI Express Generation 3 interface. So I'm going to talk now about each of the individual subsystems in detail, starting with the flexible subsystem. The flexible subsystem itself is a small on-chip network for each of the 16 flex tiles. And that network connects 4 geometry cores, which are custom processors, a local SRAM, a dispatch unit, which performs synchronization functions across the machine, and a network interface to talk to the rest of the on-chip network. The geometry cores are fixed-point SIMD processors that have specializations for molecular dynamics. For example, single instruction dot products, linear combination of vectors, cross products, even a packed complex multiply-add instruction that helps accelerate FFTs. You'll notice also that the geometry core has a large instruction cache, which helps us to execute the inner loop of our application without cache missing outside of the tile. The dispatch unit, which we've described previously in ASPLOS, provides fine-grained synchronization and improves load balancing across the geometry cores and across the machine throughout our work, during our workload. So I'll refer you to that paper for the details there. And finally, the network interface connects this local tile network to the on-chip mesh, which I'll talk about shortly. The main specialization that we've done on Anton 2, as well as on Anton, is in the high-throughput interaction subsystem, which contain fixed function hardware pipelines for computing intermolecular interactions. The main component of the HTIS, we call it, is an array, actually 2 arrays of PPIMs, which are pairwise point interaction modules. And this is just a number of pipelines that compute per cycle an interaction between 2 atoms. The PPIMs on one Anton 2 ASIC can compute 250 trillion pairwise interactions per second per ASIC. And versus Anton 1 also offer substantially increased flexibility in terms of the form of the interaction they can compute. So we are able to support much more detailed chemistry with Anton 2 than with Anton due to the flexibility in these in the Anton 2 pipelines. The HTIS also reuses the GC in a sort of a mini flex tile to perform coordination control functions, and that simplifies the software design as well versus Anton, where there was a programmable state machine for controlling the high throughput interaction subsystem. Finally, there's an interaction control block which interfaces the mini flex tile to the PPIM array, and that is responsible primarily for sequencing the streaming of particles through the PPIM array and the gathering of their forces together at the output of that array. This streaming memory can supply over 60 gigabytes per second of streaming bandwidth through the PPIM arrays. The network, the on-chip network, is also a significant change in Anton 2 versus Anton. Although the network in the machine connecting the ASICs together is still a 3-dimensional torus, the on-chip network is significantly improved, being now a mesh network instead of a ring. Overall, the on-chip network provides over 2.5 terabits per second of bisection bandwidth, and it also is a unified network in that the on-chip mesh network is part of the internode network. And so that unification provides a lot of advantages in the design and performance. And we reported that in the most recent ISCA. The interchip 3D torus network consists of 16 14 gigabit per second links per direction. And that gives us a bisection bandwidth in a 512 node machine of 57 terabits per second, which is approximately 80% of the bandwidth of the internet. A custom channel protocol and some other optimizations specific to molecular dynamics also improves performance. Finally, we also have other interfaces besides the interchip network, our host and debug interfaces. I mentioned that we moved to PCI Express Gen 3 for off-chip memory accesses. Our geometry cores can directly cache miss over PCI Express to memory mapped on the host. And we also support direct memory access. We still do have a full swing interface used for configuration and debug as well as booting. We also have an on-chip logic analyzer, which in addition to its utility for debugging, is used in-house for performance tuning. So we generate a lot of plots like this, which show the activities of the various subsystems using the logic analyzer, and try and find out where we are blocking or inefficiently load balancing in order to tune our performance. Physically, it all comes together like this. This is a die plot of the Anton 2 ASIC, and the tiled architecture is directly relevant or directly evident. The die is about 400 square millimeters in a 40 nanometer CMOS process and has about 2 billion transistors. Power dissipation is just under 200 watts, and the TDP is over 250 watts for peak use. You can see the annotated version of this. The SerDes links for the interchip network, flex tiles, 12 up here, 4 down here, and the HTIS with the PPIM arrays evident here. PCI Express interface down the bottom, and the logic analyzer over here. So there are a lot of challenges in putting together an ASIC of this size, and I thought I would focus on just one of them in this talk, and that is designing for this high power dissipation. And that drove a lot of design decisions all the way from the die up through the package, board, and system. And I'm going to cover some of those challenges now and how we dealt with them. Starting with the high power effect on the die design. So when you're designing for a high power, obviously you're concerned with power integrity. And the way that we dealt with that in the Anton 2 design was with lots and lots of metal. Over 25% of the routable metal tracks available in the process technology are used for power delivery. And in our top 3 distribution layers of metal, over 98% of the allowable metal density of the process is dedicated to power delivery. So what I show here on the right is an image of the top 3 metal layers, and you really can't tell where the routes are simply because they're so dense. If it weren't for the fact that there's one global clock line that cuts across here, and you can see that all the rest of this green is horizontal power distribution. The orange that you see along the clock line is the underlying vertical power distribution below that clock line. And you can see also a high density of connection to the bumps. We have over 14,500 core supply bumps, which makes our die photo look really uninteresting. This is all of the power delivery for the core of the chip. The only features you can really see are the SerDes here, and the PCI Express down here. And we also paid a lot of attention to cell density and decoupling capacitance placement. Within the package, we had to go and figure out how to connect and route these bumps out to the pins of the package without unduly impacting the signal integrity, which is needed for our high-speed serial links. And so we accomplished this again with lots of metal, high density of vias, and a lot of decoupling capacitors placed on the package. Our package has over 200 decoupling capacitors, and over 40% of the pins on the bottom of the package are core supply bumps, or core supply balls. You can see in the package routes, we also make sure, for signal integrity reasons, that there's no overlap between the digital power planes and the high-speed signaling planes. Beyond the package, we have to continue through the node board. 2 visually striking illustrations of the high-power design here on our individual node board are the large copper heat sink for cooling the ASIC, and the large voltage regulator module for the core power supply, which has been bench tested to over 300 watts. The circuit board itself is it's less visibly obvious, but the 24-layer circuit board has a lot of technology in it to ensure power integrity and signal integrity simultaneously. And then scaling out beyond the node board, we have the system itself. And the problem, once you get to the system where you're doing 48-volt power delivery, although it's still hundreds of amps, it's not as variable. So the power distribution doesn't become as big of a problem. What becomes a problem at the rack level is the heat removal. And so the cooling system in the rack was also heavily engineered. What you see here is opening up the back of one of our racks, 3 large blowers, 1.7 kilowatt blowers each. And overall, they move 7,600 cubic feet per minute of air through the rack. And there were detailed simulations done to make sure that each node board in the rack receives enough airflow to keep it cool. Overall, we maintain an average die temperature at our 190 to 200 watt operating power of about 50 degrees centigrade. So, in spite of all of the challenges that I mentioned in putting together a system of this scale and scope, we derive a lot of advantages from our particular application. And that enabled us to close this aggressive design with a small team. First of all, we have a well-understood workload. This is our second specialized ASIC for molecular dynamics. So not only do we derive a lot from just the fact that the workload is a single workload, but that we've done it before, and we know a lot about how it behaves. The results of our simulations are, in fact, the time-dependent positions and momenta of all of the particles in the system. So the workload itself, the output of our simulations is actually a running checkpoint, and that vastly simplifies error recovery and reliability. We have flexible frequency targets for both our cores and channels. We don't have to meet any particular protocol or operating frequency, and that gives us a lot of flexibility in physical design. Next, we're driven by performance much more than yield, and that allows us to make decisions that make our lives easier that you wouldn't necessarily make if you were trying to ship 10 million units. Versus a lot of high-performance compute applications and generalized compute applications, we have a very high computation bandwidth to I/O ratio. That aids our design significantly as well. We're obviously not concerned too much about battery life. As far as I know, we've not tried operating one of these off of a battery, but I think that that would be a rather short experiment. So that we really don't have a need to minimize standby power dissipation, and that again affects our design decisions. And finally, as I mentioned in the previous slide in the thermal design of the rack, we have a moderate and very well-controlled operating temperature. This simplifies both our timing closure and our reliability closure for the die. So where are we? And how did we get here? The Anton 2 ASIC taped out at the end of 2012, and some 4.5 months later, the first ASIC was powered on in our New York City lab. I'm delighted to report that it seemed to work completely at first power up, which is always gratifying. The first 512 node segment, we call it, pictured here, it was operational in December, as of December of 2013. We call this NYC1. And as of today, we have multiple 512 node segments in operation. Currently, we're engaged in build-out, continuing to build more machines, as well as performance tuning. Obviously, with a system this complex, a significant amount of the performance comes from how the software is put together and how well matched it is to the hardware. And that's ongoing. And finally, we are beginning to use it very recently for actual biochemistry research in-house. So I'll give you one more pretty picture. This is the same machine, NYC1, with the front doors open. And you can see here barely some of the baffling that was engineered to balance the airflow between the various boards in the rack. So, this time I'd be happy to take any questions.
Questions?
Yeah, Jeff Becker from NASA Advanced Supercomputing. So I was curious about your, I understand your choice of fixed point, but I was wondering how that affects your accuracy on the biochemistry models, especially over the large number of time steps you do.
Sure, that's a great question. So that was a question I think that we were much more concerned about with the original Anton, since we didn't have much experience with the fixed point arithmetic at the time. I think that the original Anton has shown that that is not really a problem, and partly it's because almost all of the quantities in our simulation and system can be normalized to within a nice range of fixed points. So as long as we keep quantities fairly well normalized, we actually get more precision in, say, a 32-bit fixed point operand than we would in a single precision floating point.
Okay, and the second question is, how do you get data in and out of the system? Do you have, like, where are your disks and stuff?
Oh, so that's also a good question. The PCI Express host interface is how we load data on and off the system. And if you remember, there was a figure in Momose-san's presentation, the first one, that showed that molecular dynamics, while it requires high bandwidth to internal working memory, doesn't require very large working state. And so we can actually dump our working state, the trajectory of the system, during simulation over the PCI Express interface without any problem.
Cool, thanks.
Nice talk. Generally, Huawei Technologies. Sort of follow up the second question just now, maybe silly here. So how do you boot up the system? How long does it take to boot up such a system?
How long does it take to, I'm sorry?
To boot it up.
Boot up the system?
Yeah.
Well, that's something that we're trying to optimize, particularly because there are certain molecular dynamics applications that benefit from very quickly swapping in and out state. But typically, we haven't worried about that because we tend to run the system for tens of minutes, time slice it on sort of a 15 to 20 minute basis. So the system load time, which is on the order of a minute, doesn't really impact our efficiency. Now that load time, I should be more specific, a lot of that is not actually communicating state to the ASIC, but it's a lot of other software, embedded software, system software, and queue management operations. The actual loading of state onto the ASIC and the booting is quite short, on the order of tens of seconds.
All right, thank you. Allow me another question. So if we go back to your slide number 5, I see the comparison between first generation and the second generation. Trying to figure out how do we achieve the peak throughput improvement from 2.7 to 12.7? Like we have the number of cores increased, CPU clock frequency increased, also channel bandwidth, so on and so forth. Can you give us a rough idea where each performance throughput improvement come from each of these categories?
Sure. Most of it is in most of the performance itself is in these fixed purpose pipelines. So something like 80%, I think a little over 80% of the total fixed point operation throughput is in the fixed function pipelines of the HTIS. The rest comes from the geometry cores. In terms of performance improvement, again, it's the quantity and the fact that these are doing more specialized calculations. A single interaction is anywhere from 50 to 60 fixed point operations. And so the fact that we can do them on a large quantity, over 150 pipelines and do them one per cycle, that's where most of the throughput is.
Okay, thanks a lot.
I'm Toshio from University of Tsukuba, so very impressive talk, thank you. So I have two questions. The first one is maybe related to the first questions about the precision. So you introduced some special precision system, not like a single or a double precision for the computation on the main engine. Do you, what is the main precision, numerical precision of your computation?
The precision, we work with 32-bit fixed point arithmetic.
Only?
Yes.
So there, okay, so there, I have another question that then I'm curious that what is the primary purpose of the system? Is it in enlarging the target problem size more large, or to reduce the time to solution for the fixed size of a problem?
That's a really great question. So it's a little of both. Biochemical systems of interest obviously don't follow Moore's law. Once you find something interesting, it stays the same size with time. So we're more interested in improving time to solution. somewhat also improved in, we're somewhat also interested in throughput as well, because frequently we can gather more information by sampling multiple simulations at once.
But for the purpose of that, reducing the time to solution, I think that you mean that you analyze that number of time steps up to the several femtoseconds or something on the molecular dynamics, right? So there, in that case, and I'm curious about it is satisfactory to have a 32-bit floating point precision for very long time step of the simulations of molecular dynamics.
Yes, so far the precision has not been limiting in any way that we've been able to detect over very, very long simulations.
So you confirm that numerically?
We do extensive numerical analysis to bound the error in terms of energy drift in the simulation. And yes, we limit all sources, and the sources due to the approximations made in the molecular dynamics algorithms themselves are comparable to those due to the arithmetic.
Okay, thank you very much.
Bob Stewart, Stewart Research Enterprises. Your interesting movie at the beginning showed primarily short-range interactions taking place. I'm wondering what you find in terms of the longer range, more distant parts of the molecule and its dynamical motion. Does that affect the computation much?
Okay, so if I understood your question correctly, you're asking about longer range interactions. Even the videos that I showed here have include what we would call long range interactions. And molecular dynamics is performance optimized by sort of decomposing the forces acting on an individual atom into those that are from sort of a range limited set of particles, something on the order of 10 angstroms away, and then long-range interactions from everything else in the system. So even these simulations that we have here include the effect of atoms that are anywhere in the entire chemical system on any given atom, although it is decomposed into two different methods for determining those forces.
Have you been able to determine whether or not your results look like reality?
That's an ongoing process throughout the field of molecular dynamics, but yes, we have made and published a number of studies that show that we have been able to predict quantities or behaviors of things that have been confirmed in the laboratory.
And I'm curious, who are your customers, and what applications do you see for it?
So currently we're still in the development phase, and we're not limiting ourselves to any particular customers, but right now we're just using the machine internally.
Hi, Dave Patterson from UC Berkeley. I'd just like to congratulate you for showing that computer science and computer architecture can be important for one of the most important open scientific questions in biology. So thanks for working on that. I understand in the beginning it was just the machine was for you. With Anton, are there other labs that are trying, other labs that are trying to get copies of this from you?
I don't know if I can really speak to detail on that. So far, since this machine is very new, certainly we're focused on still improving its performance, building out its capability, and using it internally. I can't really speak to the future plans.
Did Anton 1 ever get used by anybody else?
We did donate one segment, one 512 node machine of Anton, the original, to the Pittsburgh Supercomputing Center, and the grants were awarded to external researchers by the National Academies of Science for time on the machine, and a number of publications have come out of that. And our involvement was only in donating the machine and not getting involved in the grant selection process.
Thank you. Okay, one more question. We have to stay close to our schedule.
Business management professional in the crowd, Mike Brazzoni from Camp Marketing. How do you simulate it in hardware and software? What EDA tools are you using? And like Mr. Stewart and the gentleman before me, the commercial applications, is it purely for applied science in this particular application, or can these ASICs be spun to offer varying levels of performance where they might be produced in higher volume to present surely scientific opportunities for scientific research, but on a broader scale? So how'd you simulate it, your EDA tools, and really what are the commercial potentials outside the lab on a broad mass market basis? Or if you could explain what mass market might be.
So I don't think I want to go into specifically what EDA tools we used, but we did, extensive simulation and design verification from logic level simulation, gate level simulation, using architectural models, using mixes of those things, and even some experiments with FPGAs to test various parts of the design. Regarding the market, again, I can't really forecast exactly what it is that we're going to do with the machine at this point. Right now, we're entirely focused on our build out and improving performance. I think I'll leave it to people's imaginations to think about what they might do if they had one of these on their desk or in their server room.
Fantastic. Let's thank the speaker.
I also want to mention one last thing, which is we're hiring. So if anyone is interested in a job, please come to me. Thank you very much.